here with that. Okay. Well, let's see, what else do we have? Figure 4.6. Okay, so what's going on with this whole system? Well, let's see. I'm going to turn that over. That's on page 66. So you've got a cylinder shown in figure 4.6. It's supported by a vertical wall beam that is pin connected to the wall at point A and a flexible cable. Two contact surfaces with the cylinder are smooth. Sketch the free body diagram of the entire system, considering the cylinder, beam, and cable as a single body. The cylinder alone, and then C as the beam alone. So there are your, so this is what's going on here. So what do you think? If we didn't look at the book, what do you think would be going on? We'd probably have, I can find my mouse, we'd probably have tension going on here, don't we? Because it's a cable. We'd probably have some kind of a force here at A, if we're looking at the whole system, and we probably have some kind of a force here on the AX, don't we? Okay. So, and that tension would translate here. Eventually, you could say we probably have an EX and an EY. Eventually. Now that, let's put a dotted line around that, because that's, first you got to figure out what's going on here. You got to figure out what the tension is in the cable. That's probably the most important of those two. Okay. Well, let's see, what do they tell us here? Oh, was that the only thing in that figure? I guess it was. So let's go and look at this one. Oh, one other thing on that test that some of you might want to, I don't know, you might want to be a little upset with yourself. When you give me an X value, you probably ought to give me a left or right, not an up or a down. So figure that the next quiz you're going to do much better, because you're not going to do that again, right? Mark?
On the last problem, would there be a force on B going diagonal up? No.
Yeah, right there.
Oh,
Tension. Yeah. And now, if we were looking at, and we'll just look at, let's just go down there and look. See, there's the tension right there. If we're looking at the whole system, you got the tension of that cable pulling at B. Okay, but that's all you can say about that, because it's not pinned. So in this case, you won't have what you would normally think of as, okay, I'd have this and that, right? But this isn't pinned, so you don't worry about that. It's out there just floating out in space, basically, isn't it? Other than the tension of the cable. So we won't put those in there. All right? So yeah, that's, and I just put the T in there. I didn't draw the arrow. Oh, and there was something else with respect to that. Oh, on those problems, especially like on that first problem, if you just went in there and you did like negative 2100 cosine of 70, and you put the equals in there, whatever it equals, how am I supposed to know what that is? How am I supposed to know that was the force in the X? I know, right? But not everybody does. I shouldn't have to make an assumption on your quiz. Okay? So let's make sure we don't do that in the future. All of my examples, I show you how I want you to write it. And consequently, that's what the key looks like. So I think in general, you'll probably see that I took some points off for that. Okay? So that's kind of how we play the game. You can't make everybody that's checking your work assume anything. Okay? So, what else here? Anything else? So we got the tension of that cable. We've got the weight of the beam. And I tend to overlook that because we normally don't worry about the weight of the beam in this class. But that's what that is. How would we know where that's located? Well, you would have to know basically that, wouldn't you? Potentially. You got to kind of know where that's at. Okay? Then we've got the weight of that, what was that? Oh, cylinder. That's why it's C. The weight of the cylinder pushing down. Then we've got the force of the wall pushing against the cylinder, right? Then we've got AX and AY because it's pinned. And see, I don't know why they've got this weight here. I'm not sure why they're not putting some kind of a force right here. I got the wrong pin, didn't I?
Is that what's depicted below?
That's what's depicted here. And I'm not sure why they don't have it here. To be honest with you, it looks like it would be, I guess because the weight is just pushing on that, and I guess that it kind of makes you think that they would say the weight could be there, pushing down on it. But it looks like there is a reaction here somehow. But we'll go with flow, and I guess that reaction is going to show up in this bottom picture, isn't it? Right there. Well, they're showing the force of the. Yeah, if you were just studying each one of those components, this F right here is the weight of that cylinder, isn't it? But notice there's no P value there because it's not connected. That P value is actually from the wall, isn't it? So I guess that essentially that's going to be taken care of right here eventually. Here and up here. But this is getting down the road. This is later on in this chapter and the next one, as far as splitting that out. What we're going to be dealing with right now, the first thing we're going to deal with is just what's going on for the whole system. Okay? Then we'll go and start breaking it out. So don't panic on that just yet. Okay, then what? Let's see. Too far. Oh, that baby took off. All right, two-force member. And this is shown on page 67, equilibrium of concurrent force systems. So what's going on here? Well, not a whole lot. But what you can say about this is it's a longitudinal axis of the member, so you're going along here, and you've just got two forces pushing against each other, if you will. The thing that this screams to me is that this member is in compression. Because the forces are both pushing in on it. Okay. Now, the one thing you have to note there is, for this thing to stay static, those two forces have to be opposing each other, don't they? They either have to be pushing against each other or pulling away from each other. So, and maybe that's the one thing that I think they're probably looking at there. So just keep that in mind. Okay, then let's see. We got the next figure. Well, what do we got here? Boy, that looks an awful lot like what we've just been through, doesn't it? What they're showing you there is you can draw that triangular shape, if you will, to get the resultant force. I'm not going to worry about that too much in this picture over here. That's just taking these three and stacking them up, isn't it? You're taking this one coming out. This one's actually, is that pointing to the left or to the right? Yeah. This one's coming out, that one's going up, and your result is this right here. So again, no need to worry about that as far as I'm concerned. All we're going to worry about in this case is we're going to have a force doing this that's probably going to be pulling back this way. We're going to have a force doing that, and that would be OY, wouldn't it? OX. We've got a tension in this cable right here that we know is 30 degrees off the horizontal axis, and then we've got this force right here, which is 100 pounds. That's all I'm worried about. Okay. Well, I'll have to worry about more than that. I'll have to worry about some distances to be able to do all the calculations on this. Okay. But that free body diagram, yeah, it's going to look like this. Oh, yeah, I still think, actually that's not going to go to the left. It's got to go to the right, doesn't it? If that wall doesn't push back, then that thing's going to keep going. So that's OX. Just like OY has to go up. Then we've got 100 pounds here. Tension in this cable. And what I would say there is the tension in RQ. Is that cable's labeled RQ, right? So I would say the tension in RQ. Then you would have to give the angle right here. And then we also would need this distance. And we would potentially need that distance there. Okay? Eventually what would come into play there would be something about a moment. So we'd have to have the distances. Alright? Let's see what else here. So we got that one. I want to get to where we can start figuring out what some of those numbers really are. To the fun stuff. Equilibrium of concurrent forces. You know, let's see. On that, they actually did do a little bit of work on that last problem. Let's hold off on that. Let's see. That's 410. Okay, that's a similar type thing going on there. I'm gonna go back, pick up something else here. Okay, 411. What we got going on here? And again, we just got some. What's the free body diagram of that going to look like? If we did the free body diagram of that, it's going to look like this. Where those two pin members basically look like one, if you will, and we'll treat them as one. We've got, and those are given, right? Yeah, 1,800 pounds going this way.
What page you on?
71. And we've got 2,000 going this way. We've got, it's pinned at A. So now I'm going to guess that AX is going to the left in this case. And I'm going to guess that AY is going down. Just backwards of what we just got done telling you, isn't it? Well, point C is pinned as well. So I'm going to guess that CY is going up. CX I'm going to guess is going to the left. Now, you know what, though? C or AX. Yeah, I'm going to guess. I'm going to leave my guess at that. Okay, and then we would also note that this is 45 degrees and that this is 60. Okay, and then normally we would give some distances here and a distance to the middle and then probably a distance here.
How are you coming up with the direction? Why is AY?
Well, right now I'm just guessing. But the reason I'm guessing that AY is going down is because, let's look at this. If this thing is pinned right here and this is pulling, isn't this trying to pull that up out of the ground?
Okay. I didn't look at that. It's going to the right.
But that illustrates the point. And it's just like when I was overlooking the weight of the beam in that one example. You have to look at these problems and make sure you get every force. And people were forgetting that on that last problem we did the other day. They were leaving parts of that out. Okay, not really leaving it out, but they were neglecting it on force in the X. One of those forces was going at an angle, wasn't it? You have to do X and Y in that case. Okay. Well, same thing here. We have to make sure that we're getting all the forces that are either forces that were supplied or forces that we think are going to happen based on the fact that it's pinned or anchored somehow, if you will. Okay, so we have to be very, if I can say, vigilant on that and make sure that we get everything.
So
Okay.
you're needing what you drew in the free body diagram plus what they have as figure B in figure 411?
It would be,
Like what-
well,
what they have below.
they're doing that a little bit different.
They did just
Right.
pin B,
But we're going to do it, we're going to look at the whole system.
so we need both of those on a test typically.
Well, they're jumping, from my perspective, they're jumping a little bit ahead with that B part.
Okay.
Because that's when we start dealing with analyzing structures, we'll actually have to go back. We'll have three different ways we can do it. We can do method of members, method of joints, and then method of sections. And what they're doing in B would be a method of joints. Okay? So they're only analyzing point B, or that joint. Yeah. But in that case, that will tell you everything that's going on in that bar from A to B, and then from the bar from B to C. It'll show you what's going on there. Then you can go back and find out what you need at those reaction points. Okay? Josh?
Shouldn't CY be going down?
I don't know. But think about it. If this thing is pinned, I don't know, and I honestly don't know. I'm not messing with you. I don't know because I don't have enough information to solve that problem at this point. Not having any of those distances. But my perspective on that, the reason I say that is from an educated guess, if you will, and it could still be wrong, but think in terms of that this is pinned over here, and these forces are pulling this way and pushing down, more than likely this member is going to be in compression, isn't it?
Yeah.
If it's in compression,
Right, I see that.
then this is probably going to have to push back up.
Right.
Because if a member is in compression, what that looks like is this. Compression looks like this, and tension, well, I just did that backwards. Compression, well, in this case, compression is going to be pushing right down on that at point C. This is compression. If for some reason it were in tension, it would look like this. Okay? So it's in compression, so it's pushing back down on C, so I'm thinking that C is going to have to do that. Okay, and then it's also going to have to do that. But the beauty of it is, like I said, if we make the wrong educated guess, when we do our sum the forces in the X, sum the forces in the Y, just like we've been doing to this point, the answer will come out right, but it'll be a negative value. And then we know, doggone it, we picked the wrong one. As smart as we are, we picked the wrong one. And it can happen to anybody. I mean, there's sometimes you just cannot tell what it needs to be. But in this case, I thought, well, I think I can kind of get a pretty good guess on it. I might be wrong, I don't know. I've been wrong before, once or twice. Because I think I was wrong a couple times this last weekend. I hate being wrong on holidays with a passion. Well, I really hate being wrong anytime, but